A spacecraft built to find alien planets just photographed something it was never designed to see. A bright dot, moving, with a tail streaming behind it, racing through our solar system right now from another star system, and NASA captured it 2 months before anyone even knew it existed. If you love space mysteries, hit that like button and subscribe. What we are about to discover gets stranger every minute. Take a breath. We launch now. Picture a satellite the size of a washing machine, floating 350,000 miles above Earth, cameras locked on thousands of stars, all at the same time. This is TESS, the Transiting Exoplanet Survey satellite, launched in 2018 with one job: find planets around distant stars, worlds we have never seen, solar systems we can only imagine. The technique is simple but brilliant. TESS watches a star, waits for a tiny dip in brightness. That dip means something crossed in front of it. A shadow, usually a planet blocking the starlight for a few hours. Like watching for a moth crossing in front of a streetlight. The light dims slightly. You know something passed. You can measure its size from how much light disappeared. You can calculate its orbit from how often it happens. But to catch these planetary shadows, TESS needs to watch massive sections of sky, thousands of stars, continuously, for weeks at a time, recording every flicker, every change, every unexpected movement. That wide field of view sees everything: planets crossing stars, asteroids tumbling through space, distant galaxies exploding, comets with tails, things that move, things that change, things that absolutely should never be there. The satellite scans the same region for about 30 days, every detail captured, every variation logged, millions of images stored in archives back on Earth. Scientists comb through the data hunting for patterns, looking for those telltale dips in starlight, the signature of a planet. But sometimes they find something else entirely, something moving too fast, something with a glowing tail, something traveling in the wrong direction. In January 2026, TESS was doing exactly what it always does: hunting planets, watching stars, recording absolutely everything in its view. Then, an astronomer noticed something unusual in the latest batch of data: a bright dot, moving steadily across the starfield, and behind it stretched a faint tail of light. Planets do not have tails. Planets do not move like that across the background stars. This was something different, something unexpected. The researchers ran calculations, checked the trajectory, analyzed the speed and direction, measured how fast it was traveling relative to our solar system. Their conclusion seemed impossible at first. This object came from somewhere else, from interstellar space, from the region between stars, from another star system entirely. They gave it a designation, 3I Atlas, the third confirmed interstellar object in human history, out of millions of asteroids tracked, thousands of comets catalogued, decades of careful observations. Only 3 visitors from beyond, and TESS just accidentally caught one passing through our neighborhood. But here is where the story gets truly weird. That discovery in January was actually just the second time anyone noticed this comet. The first time? Nobody realized what they were looking at. Scientists never delete space telescope data. Every image TESS captures gets saved, archived, made available for researchers worldwide to search through. After identifying the interstellar comet in January, astronomers started wondering, could TESS have seen it earlier? Was there any previous record of this visitor hiding somewhere in the archives? So they went digging, searching through months of old observations, looking for any earlier glimpse, any faint trace, any sign this traveler had already passed through the field of view. What they discovered changed the entire timeline. The comet was already there, already photographed, already sitting in the data from May 2025. 2 full months before its official discovery in July, TESS had captured it, recorded its position, measured its brightness, all while it was still approaching our inner solar system, still weeks away from anyone noticing it existed. But nobody saw it at the time. The comet appeared as just another faint dot among millions of stars, easy to overlook, easy to dismiss as background noise or a distant asteroid. Finding it required stacking multiple images together, watching for anything that moved between frames, filtering out the fixed stars, removing cosmic rays and other interference, looking specifically for objects that changed position over time. There, a faint streak in the stacked images, consistent motion across multiple nights, a barely visible tail extending from the bright core. The research team matched it perfectly to the comet found in January. Same trajectory, same brightness pattern, same exact object, just captured weeks and weeks earlier than anyone knew. This retroactive discovery answered crucial questions. When did the interstellar visitor actually enter our detection range? Much earlier than expected. How long had we been photographing it without knowing? At least 8 weeks. But the finding also raised deeper mysteries. What else might be hiding in those vast archives? What other visitors passed through without us noticing in real time? How many interstellar objects have we accidentally photographed but never identified? The archives contain years of continuous observations, billions of individual images, countless frames of star fields. Most have never been thoroughly searched for fast-moving interstellar travelers. This comet might have company. Other visitors could be sitting there, already recorded, already captured, just waiting for someone to look in exactly the right way. For now, though, researchers had one confirmed target, one interstellar object still within reach, and it was racing away from us, fast, heading back toward the depths of interstellar space. If they wanted to study it properly, they needed to move quickly. Every day it traveled millions of miles farther. Every week it grew dimmer. Every month it became harder to observe. The clock was ticking, and this was humanity's chance to learn from a visitor from the stars. But first, they needed to understand just how rare this opportunity really was. Only 3 confirmed interstellar objects in all of human history. Think about that number for a moment. Millions of asteroids catalogued, thousands of comets tracked, centuries of watching the skies. Just 3 visitors from beyond our solar system. The first one arrived in October 2017, tumbling through space at an incredible 54 miles per second, moving so fast our gravity could barely deflect its path. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger sent from the distant past, because whatever this object was, it came from somewhere far away and long ago. Oumuamua looked strange from the very beginning, long and thin like a needle or cigar, about a 1/4 mile in length, spinning end over end every 7 hours. Nobody had ever seen an asteroid shaped quite like that. Most asteroids are lumpy and roughly spherical, potato-shaped, formed by collisions and gravity pulling them into rounded forms. Oumuamua looked stretched, elongated, almost artificial in its proportions. Then, it did something that shook the entire scientific community. It accelerated, sped up as it left the solar system, without any visible rocket, without any obvious source of thrust. Scientists scrambled for explanations. Maybe frozen gases were vaporizing from its surface, pushing it forward like a tiny rocket, outgassing they call it, common in comets approaching heat sources. But Oumuamua showed no visible tail, no cloud of gas and dust, no debris trail, nothing to explain where the acceleration came from. Some researchers suggested radical ideas. Could it be an alien probe? A spacecraft from another civilization? Designed to explore star systems and powered by technology we do not understand? Others argued for natural explanations, a weird comet, an unusual asteroid, something formed under conditions we have never encountered before. The debate continues today. Oumuamua left our solar system before we could get close enough for detailed study. Gone, vanished back into interstellar space, taking its secrets with it. Then came visitor number 2, August 2019, another interstellar object, but this time clearly and obviously a comet. Gennady Borisov, an amateur astronomer in Crimea, spotted it first, so they named it 2I Borisov in his honor, the second confirmed interstellar visitor. Unlike Oumuamua, this one looked familiar, a ball of ice and rock, glowing brightly, shedding gas and dust as it heated up near our star, behaving exactly like comets are supposed to behave. Scientists felt relieved. Finally, a normal interstellar object, something that made sense, something that fit their models and predictions. But when they analyzed its chemical composition, they found something odd. The comet contained far more carbon monoxide than any comet from our solar system, way more than expected. The ratio was all wrong, like it formed in a much colder environment, around a different type of star, under completely different conditions than anything in our neighborhood. Borisov also moved incredibly fast, too fast for our gravity to capture. It swung past our star, made a long curved turn, and headed back out toward interstellar space without slowing down. Both visitors came and went quickly, brief appearances, barely enough time for proper study, then nothing for years. No new interstellar objects, no new visitors, until this comet appeared, the third one, the newest one. And this time, NASA had multiple spacecraft ready, multiple telescopes prepared, multiple teams coordinated to capture every possible detail. This was humanity's third chance, and maybe the best chance yet. January 15th, 2026, NASA initiated a special observation campaign. TESS would track the interstellar comet continuously, not just snapshots, hours of uninterrupted footage, detailed measurements of every change in brightness. The goal was specific and crucial. Measure how the comet's brightness varies over time. Watch for patterns in those variations. Figure out how fast the nucleus spins. Determine its rotation period. Why does rotation matter so much? Because it reveals fundamental truths about structure and composition. A fast-spinning comet is probably dense and solid, strong enough to hold together under the stress of rapid rotation, gravity and internal strength keeping it intact. A slow-spinning comet might be loosely packed, fragile, held together by weak gravity rather than structural rigidity, more like a rubble pile than a solid rock. The rotation rate would tell researchers which type they were dealing with, and that would indicate something profound about where it came from, how it formed, what kind of stellar environment created it billions of years ago. TESS began its observations right on schedule. Cameras locked onto the target, recording frame after frame, building up hours of continuous coverage. Then disaster struck. On January 15th, just as observations began, TESS suddenly entered safe mode, an automatic shutdown procedure. The spacecraft detected an issue with its solar panels and immediately protected itself by halting all science operations. Safe mode meant no observations, no data collection, no cameras recording. Everything paused while engineers on Earth diagnosed the problem. The science team held their breath. How long would this last? Would they lose their opportunity? Would the comet slip away before TESS came back online? Time was everything. The comet was not waiting around. It traveled farther from us every single hour. Every day it moved millions of miles deeper into space. Every week it grew fainter in the cameras. They desperately needed that rotation data, needed those brightness measurements, needed to catch the pattern before the comet became too dim to observe properly. 3 agonizing days passed. January 15th to January 18th, engineers worked around the clock, diagnosing, testing, carefully bringing systems back online one by one. Finally, TESS recovered. Solar panels functioning normally, cameras operational, observation systems ready. The spacecraft resumed its mission. The team immediately repointed at the comet. No time to waste. Every remaining hour counted. They needed to make up for those 3 lost days. Over the next several days, TESS collected 28 hours of continuous footage. The comet moving steadily across the star field, frame by frame, pixel by pixel, each image separated by just 2 minutes. Researchers at MIT compiled those hundreds of frames into a time-lapse video, a movie showing the comet's journey across the sky. Stars remaining perfectly fixed in the background, the comet moving like a bright dot, dragging its faint tail behind it. In the footage, you can see it clearly. The comet appears brighter than the surrounding stars. The tail stretches faintly in the opposite direction from our star, exactly as expected from radiation pressure pushing gas and dust outward. And buried in those 28 hours of observations, hidden in the subtle changes in brightness, was the pattern they needed, the key to understanding this visitor's spin. But first, they had to extract that pattern from the noise, measure it precisely, calculate exactly what it meant. Astronomers measure brightness using a backward scale called magnitude. Lower numbers mean brighter objects, higher numbers mean dimmer ones. It confuses everyone at first. The brightest star in our night sky, Sirius, sits at magnitude -1.4. Full moon shines at magnitude -12.7. Our own star blazes at magnitude -26.7. Meanwhile, the dimmest objects visible to the unaided human eye reach about magnitude 6. Anything fainter than that requires optical help, binoculars, telescopes, long exposure cameras. The Interstellar Comet measured at magnitude 11.5, about 100 times fainter than the dimmest stars you can see without equipment, invisible to the naked eye completely. You would need a decent amateur telescope to spot it, nothing professional grade, just enough light gathering power to pull faint objects out of the darkness and make them visible. TESS was not using a normal telescope. It uses 4 wide-field cameras, each one designed to watch huge sections of sky simultaneously. Together, they can monitor thousands of stars at once. Those cameras captured the comet beautifully. Even at magnitude 11.5, even with thousands of background stars crowding the field, the comet stood out clearly in every frame. And the brightness changed, subtly, rhythmically. Following a clear pattern, the comet would get slightly brighter, then dimmer, then brighter again, over and over in a consistent cycle. This meant rotation. As the nucleus spun, different surfaces faced toward TESS. Some surfaces reflected more light than others. Maybe they had more ice. Maybe they were smoother. Maybe they faced the optimal angle. Scientists measured each cycle carefully, timed how long each brightness peak lasted, calculated the exact period of rotation. The numbers revealed something important. The comet was spinning steadily, rotating in a regular pattern, no wild tumbling, no chaotic wobbling, just smooth, consistent rotation like a planet turning on its axis. That indicated structural integrity. The nucleus was holding together well. Recent collisions had not shattered it. Tidal forces had not torn it apart. Whatever this object was, it remained intact and stable. But rotation also revealed something else crucial. The comet was extremely active, shedding significant amounts of gas and dust, the material vaporizing from ice deposits deep inside. As the nucleus spun, jets of gas erupted from the surface, carrying dust particles with them, forming the visible tail. The tail always pointed directly away from our star because radiation pressure pushed it outward into space. The amount of gas told scientists how much ice was vaporizing, how much mass the comet was losing every day, how active this interstellar visitor really was. Turns out, very active, surprisingly active, throwing off material at rates comparable to comets born in our own solar system. Despite traveling through interstellar space for millions of years, despite the unimaginable cold of the void, this comet still contained enough volatile ices to create a spectacular tail. TESS was not the only spacecraft watching. Far from it. This was a coordinated observation campaign involving multiple missions across the solar system, each one adding unique data, each one capturing different details. Hubble's Space Telescope pointed its sharp eyes toward the visitor, captured high-resolution images of the nucleus and coma, the fuzzy cloud of gas surrounding the core. Hubble could see details TESS could not. Structure, texture, variations in the tail. Parker Solar Probe, deep in the inner solar system where temperatures reach thousands of degrees, caught a glimpse as the comet passed through its field of view, adding another data point, another angle, another perspective. JUICE. The Jupiter mission, currently cruising toward the outer solar system, turned its instruments toward the comet during a brief observation window. Every spacecraft that could contributed something. Together, they were building the most complete picture of an interstellar object ever assembled. Brightness, rotation, composition, structure, behavior. What they learned was both familiar and strange. This comet looked normal, acted normal, behaved like comets from our solar system, except for one impossible fact. It came from somewhere else entirely. Where exactly did this comet come from? Nobody knows, and maybe nobody will ever know. Scientists traced its trajectory backward through space, calculated where it had been millions of years ago, ran the numbers through sophisticated orbital models. The answer they got was frustratingly vague. Somewhere in interstellar space, somewhere beyond our solar system, somewhere among the thousands of nearby stars. But which specific star? Unknown. Tracing objects backward through time gets exponentially harder with each passing millennium. Stars move, orbits shift, gravitational interactions change trajectories. Over millions of years, everything drifts and changes. Finding which star system this comet came from is like trying to figure out where a specific drop of ocean water originated. Theoretically possible, practically impossible. The comet could have formed around any of 10,000 nearby stars, or it could have traveled much farther, from a star so distant we cannot even see it clearly from Earth. What we can calculate is roughly how long it has been traveling, millions of years minimum, possibly tens of millions, maybe even longer, depending on its exact path. Think about the scale of that journey. This frozen ball of ice and rock has been drifting through interstellar space for longer than modern humans have existed, longer than most species on Earth have been around, longer than the last ice age. It has passed through regions of space we will never visit, traveled near stars we can barely imagine, survived conditions we can barely comprehend, all while spinning silently through absolute darkness. And now it is here, briefly passing through our neighborhood, a visitor from deep time and deep space, just another waypoint on an endless journey. The comet will not stay long though. It is already leaving, already moving away from our star, already heading back toward the outer reaches of our solar system. Its velocity tells the story. 26 miles per second relative to our star, fast enough to escape our gravity completely, no chance of being captured, no possibility of settling into a long-term orbit. It came from interstellar space. It will return to interstellar space. That journey is inevitable and unstoppable. In a few years, the comet will cross beyond Neptune, the outermost major planet, the edge of the region we consider our planetary neighborhood. After that comes the Kuiper Belt, a vast donut of icy bodies extending billions of miles from our star. Billions of comets, billions of frozen chunks, all the leftovers from when our solar system formed. The visitor will pass through all of it. moving steadily outward, never slowing, never stopping. Then the Oort cloud, a spherical shell of trillions of comets surrounding our entire solar system, extending nearly halfway to the nearest star, the absolute frontier of our gravitational influence. The comet will pierce through that shell too, emerging on the far side, entering true interstellar space once again. And it will keep going for millions more years, drifting through the void until perhaps it encounters another star system, another family of planets, another world with astronomers scanning the skies. Maybe billions of years from now, some other civilization will spot this comet passing through their system, wonder where it came from, try to trace its origins, just like we are doing now, but they will never know it came from here, never know we saw it, never know we studied it and wondered about its journey. That is the nature of interstellar visitors. They connect star systems across space and time, but they carry no messages, no information about where they have been or what they have seen. They are just ice and rock, spinning through eternity. Comets are frozen time capsules, preserved records of the conditions that existed when they formed, ancient samples from the birth of star systems. When a new star ignites, it creates a swirling disk of gas and dust around itself. Planets eventually form from that disk, gradually accumulating material, growing larger through countless collisions. But some material never gets incorporated into planets. Some chunks remain frozen far from the star, unchanged, unmelted, untouched for billions of years. Those frozen chunks become comets, repositories of the original material, chemical fossils preserving the exact composition of that ancient disk. Our solar system contains billions of comets. Most lurk in the Oort cloud, far beyond the planets, frozen solid, dormant, waiting, unchanged since our star system formed 4.6 billion years ago. When we study a comet from our solar system, we learn about our own history, about the conditions that existed when Earth formed, about what materials were available, about the chemical environment that created our world. But this interstellar comet, it carries the history of a completely different star system, a different disk, a different set of conditions, different chemistry, different temperatures, different everything. By analyzing the gases it sheds, scientists can determine what elements were present where it formed, how much carbon versus oxygen, what ratios of hydrogen to heavier elements, what kinds of ices dominated. Those ratios reveal profound truths about the temperature in that ancient disk, about the pressure, about the size and type of star, about how planets might have formed there. In a sense, this comet is a messenger, carrying physical samples from a place we can never visit, a star we may never identify, a world billions of miles away that existed billions of years ago. The comet has no awareness of this role. It is just ice and rock, spinning mindlessly through space, reflecting light, shedding gas, following the laws of physics. But to us, that frozen ball represents something priceless, a tangible connection to another star system, a real sample from beyond our home, proof that the galaxy is connected. Every spectrum scientists capture adds new information. Every chemical signature identified reveals more about that distant stellar nursery. Every measurement brings deeper understanding. What they are learning is simultaneously humbling and exciting. The universe does not consist of isolated islands. Star systems are not separate bubbles cut off from each other. Material flows between them. Comets get ejected. Asteroids get thrown out. Maybe even larger objects we have not detected yet. Maybe rogue planets. Maybe things stranger still. This comet proves the flow is real. So did Oumuamua. So did Borisov. 3 confirmed examples of interstellar exchange. 3 pieces of evidence that the galaxy is interconnected. Most objects ejected from star systems never encounter another one. The distances are too vast, the targets too small, They drift through the void forever, unseen, unknown, lost in the darkness between stars. But a tiny fraction pass close to other systems, close enough to be detected, close enough to be studied, close enough to teach us about their origins. This is humanity's third such encounter, third glimpse of material from beyond, third opportunity to learn about the diversity of stellar environments. And every time we catch one, the galaxy feels slightly less empty, slightly more connected, slightly less lonely. TESS was never designed to find comets. The mission was built specifically to discover exoplanets, worlds orbiting distant stars, Earth-sized planets, Neptune-sized planets, giant Jupiter-sized planets, anything that transits across stellar disks. But space missions rarely accomplish just their primary objectives. Engineers build spacecraft with flexibility built in, extra capabilities, backup instruments, redundant systems, because you never know what you might discover. TESS carries wide-field cameras perfect for planet hunting. Watch thousands of stars, catch the tiny dips in brightness, identify the planets. But those same cameras are also perfect for tracking fast-moving objects. Comets, asteroids, anything crossing the field of view, anything changing position between frames. The data archiving system was designed to keep every observation forever, make it publicly available, let anyone search through it, because the original mission scientists might miss things, might overlook something important, might not think to look for certain patterns. Those design choices made finding the interstellar comet possible, not because anyone planned for it specifically, but because the tools existed, the capability was there when needed. This happens constantly in astronomy. A telescope built for one purpose discovers something completely different and equally important. Hubble was designed to study distant galaxies, measure cosmic expansion, probe the deep universe. But it also revolutionized our understanding of exoplanet atmospheres, dark energy, star formation, stellar evolution. James Webb Space Telescope was built to observe the first galaxies, the earliest stars, the dawn of cosmic time. But it also studies exoplanet atmospheres, maps chemical compositions, tracks weather patterns on alien worlds. TESS was built to find planets. Now it tracks interstellar comets. That flexibility matters enormously, because we cannot always predict what we will find, cannot always anticipate which discoveries await, cannot plan for every possibility. Nobody predicted Oumuamua would appear in 2017. Nobody expected Borisov in 2019. Nobody planned for this comet in 2025. But when they appeared, humanity had the tools ready, the telescopes operational, the detection systems functional, the expertise prepared. And that preparedness let us observe them, study them, learn from them, extract every possible piece of information before they vanished back into the darkness. This comet is changing how astronomers think about interstellar objects, about how common they might actually be, about what we can learn from systematic searches. Before Oumuamua, interstellar objects were purely theoretical, predicted by models, expected from simulations, but never actually confirmed, never directly observed. Now we have 3 confirmed examples in less than 10 years, 3 visitors documented, 3 opportunities seized. That suggests they are not rare at all. They are probably passing through constantly. We just missed most of them, failed to notice, failed to look carefully enough. The key is better detection, more sensitive instruments, smarter search algorithms, more thorough examination of archival data. When we improve those capabilities, we will find more, dozens, maybe hundreds, each one carrying unique information, each one revealing something new about the galaxy, each one proving that our solar system is not isolated, that we are connected to the rest of the cosmos through these wandering messengers. The January observations finally ended. TESS collected its full dataset. Scientists began the detailed analysis, extracting patterns, measuring variations, calculating rotation rates. But the observation campaign was far from over. Other telescopes continued watching, tracking the comet as it moved steadily farther from our star, growing dimmer, fainter, harder to detect with each passing week. Ground-based observatories around the world pointed their instruments skyward. Large professional telescopes, university research facilities, even some amateur astronomers with good equipment. They captured spectra, broke the comet's light into its component wavelengths, analyzed which colors appeared bright and which appeared dark, each pattern revealing specific chemicals. Water, frozen water vaporizing into space, the same molecule covering 70% of Earth's surface, the same substance filling our oceans, found now in a visitor from another star system. Carbon monoxide, a simple molecule, one carbon atom bonded to one oxygen atom, common in comets everywhere, common in interstellar space, found here in expected quantities. Ammonia, 3 hydrogen atoms bonded to one nitrogen atom, another common comet component, another frozen ice sublimating in the heat. Methane, 1 carbon bonded to 4 hydrogens, natural gas, simple hydrocarbon, present in small amounts. Hydrogen cyanide, a more complex molecule, poisonous to humans, common in space, formed in the cold depths of molecular clouds. Everything seemed normal. Everything matched expectations. Nothing unusual, nothing obviously alien, just standard comet materials found throughout the cosmos. But the ratios were slightly off. The proportions did not exactly match what we measure in solar system comets. Close, very close, but measurably different. More carbon monoxide than typical, less water ice than average, slightly different ammonia levels, small variations, subtle differences, but real and detectable. Those differences matter tremendously. They indicate the comet formed under different conditions, around a different type of star, in a colder or hotter region, with different available materials. The variations teach us about stellar diversity, about how planet formation changes depending on circumstances, about what elements dominate in different environments. This comet is one data point, one example, one sample from one unknown star system. But it is an incredibly valuable example. Every interstellar object we study adds to the picture, fills in details, provides constraints, answers questions we never thought to ask, raises new questions we never imagined. Like, why do interstellar objects seem to arrive in clusters? Oumuamua in 2017, Borisov in 2019, this comet in 2025. Is that the actual pattern, or are we simply getting better at finding them? Better telescopes, better algorithms, better awareness? Probably the latter. Our detection capabilities improve every year. Our search strategies get smarter. Our telescopes grow more sensitive. Our data processing becomes more sophisticated. We are not seeing more interstellar objects because more are arriving. We are seeing them because we finally developed the tools to notice them, the expertise to identify them, the systems to track them, which means the floodgates might be opening, the trickle becoming a stream, the rare becoming routine. In 10 years, we might catalogue dozens of interstellar visitors. In 20 years, perhaps hundreds, each one teaching us something new, each one connecting us to the wider galaxy. But that future requires continued investment, better telescopes, dedicated search programs, automated detection systems, scanning the skies constantly. The technology exists, the expertise exists, the desire exists. We just need to commit to watching carefully, to searching thoroughly, to never assuming we have seen everything. Because the galaxy has more visitors to send, more messengers to deliver, more stories to tell. Imagine a future where detecting interstellar objects becomes completely routine, where astronomers catalogue dozens every single year, where we track their orbits, measure their compositions, build comprehensive databases, where we do not just watch them pass by from billions of miles away, where we send actual spacecraft to intercept them, to fly alongside them, to land on their surfaces, to drill samples and bring pieces back to Earth. That future is not science fiction. The technology exists right now. The mission concepts have been designed. The proposals sit waiting for funding and approval. Several space agencies have drafted interstellar object intercept missions. Fast spacecraft, always ready, sitting in orbit, waiting for targets to appear. Engines ready to fire. Trajectories pre-calculated for various approach angles. When a new visitor is detected, the spacecraft launches immediately, accelerates hard, burns fuel without hesitation, races to catch up before the target escapes our reach. Once close enough, the spacecraft activates its full instrument suite. Cameras capturing high-resolution images, spectrometers analyzing surface composition, radar mapping internal structure, drills extracting physical samples. Then, the spacecraft returns, carrying pieces of the interstellar visitor back home. Samples we can analyze in laboratories, touch with actual hands, study with every instrument we possess. That is the dream. And it is closer than most people realize. The engineering challenges are understood. The mission architectures are feasible. The costs are acceptable. We could do this within the next decade if we committed to it, could intercept the next Oumuamua, could return samples from the next Borisov, could revolutionize our understanding of interstellar space. But for now, we rely on remote observations, telescopes watching from afar, cameras capturing reflected light, spectrometers analyzing chemical signatures from millions of miles away, and those tools are remarkably powerful, more capable than most people appreciate. Modern astronomical instruments can extract astonishing amounts of information from faint, distant objects. TESS proved that beautifully. A satellite designed for planet hunting successfully tracked an interstellar comet, measured its brightness variations, revealed its rotation period, all from hundreds of thousands of miles away, never getting anywhere near the actual object. That is the power of modern observational astronomy. You do not need to touch something to understand it fundamentally. You just need to observe it carefully, measure it precisely, analyze the light it reflects or emits. Light carries information encoded in wavelengths, in brightness, in polarization, in timing, in spectral lines. All of it tells a detailed story about composition and structure and motion and history. Scientists are experts at reading those stories, at extracting meaning from the faintest signals, at finding patterns in apparent noise, at determining truth from photons. This comet is now too faint for most telescopes, too distant for detailed study, too dim for spectroscopy. But we still extracted enormous amounts of data while it was observable. Every image captured contributes to the dataset. Every spectrum analyzed adds chemical knowledge. Every brightness measurement refines our understanding of rotation and structure. When the comet finally fades completely from view, astronomers will possess the most comprehensive dataset of an interstellar object ever assembled, a reference for all future discoveries, a benchmark for comparison. And somewhere out there, the next visitor is already approaching, already traveling toward our solar system, already bringing new mysteries and new lessons. We just have not detected it yet, have not noticed it crossing through our telescope fields, have not recognized its unusual trajectory, but we will, eventually, when it gets close enough, bright enough, obviously different enough. And when we do, all the lessons from this comet will guide our observations. All the techniques refined here will be applied immediately. All the expertise gained will maximize what we learn. Each interstellar visitor teaches us how to study the next one better, how to extract more information, how to ask smarter questions, how to recognize what matters. The learning compounds, the capability grows, the understanding deepens. This is just the beginning. Interstellar objects are not invaders threatening our world. They are not harbingers of doom. They do not carry diseases or dangers. They pose no threat whatsoever to Earth or humanity. They are simply travelers, wanderers passing through on journeys that began long before humans existed and will continue long after we are gone. They change nothing about our solar system, do not disturb planetary orbits, do not alter the balance of forces, do not affect anything meaningful about our cosmic neighborhood. They just pass through, briefly visible, temporarily within reach, then gone again into the darkness. But they matter enormously, because they prove beyond doubt that our solar system is connected to the rest of the galaxy, that we are not isolated, that material flows between stars. For most of human history, we imagined our solar system as separate and alone. An island of planets orbiting our star, surrounded by infinite emptiness, cut off from everything else in the cosmos. We knew other stars existed, could see them twinkling in the night sky, but they seemed impossibly distant, unreachable, separate, having nothing to do with us. Interstellar objects shatter that illusion completely. They prove the galaxy is interconnected, that material moves between stellar systems, that we are part of something vast and dynamic. This comet traveled millions of years to reach us, not intentionally, not by design, not carrying any message or purpose. It was simply ejected from its home system, thrown out by gravitational interactions. Maybe a close encounter with a giant planet, maybe a near miss with a passing star, maybe something stranger, and it drifted through the cold, through the dark, through regions of space humans will never visit for millions upon millions of years, until purely by chance it happened to pass near our star, near our planets, near our world, with its astronomers and telescopes and curiosity. By pure cosmic luck, we were watching when it arrived, had the tools ready, possessed the knowledge to recognize what we were seeing. That chance encounter taught us something profound and beautiful. The universe is full of wanderers, full of travelers moving between stars, full of connections we are only beginning to discover. This comet is one story among countless billions. Oumuamua, another. Borisov, a third. How many more are drifting through the galaxy right now? How many have we missed? How many will we eventually find? We do not know the answers yet, but we are looking now, really looking, with better tools and deeper understanding and greater determination. And every time we find a visitor, the galaxy feels smaller, more connected, less empty, more alive with motion and exchange. We are not alone in the void. We are surrounded by wanderers, by frozen messengers, by travelers carrying samples from other stellar environments. And we are finally learning to read what they tell us, to decode their chemical signatures, to understand their trajectories, to appreciate their journeys. The comet does not care about any of this, cannot care, has no awareness or intention or purpose. It is just ice and rock, spinning through space, following physical laws, reflecting light. But to us, it represents something magnificent. A connection across the gulf of interstellar space, a sample from another world. A reminder that we are part of the cosmic whole. Let me tell you what happens next to this wandering visitor from the stars. Right now, as you listen to these words, the comet continues moving outward, away from our star, away from the inner solar system, away from the warmth and light. In a few months, it will become too faint for most ground-based telescopes to detect. Only the largest professional observatories will still track it, giant mirrors collecting every possible photon, cameras exposed for hours to capture enough light. In a few years, even those magnificent instruments will lose sight of it. The comet will fade into the background, indistinguishable from distant stars, swallowed by the darkness. Then it will truly be gone, out of reach, beyond our capabilities, vanished from human knowledge. But the data remains, the images, the spectra, the measurements, the observations. Everything collected during its brief period of visibility. Scientists will study that data for years, probably decades, analyzing it with improving techniques, extracting new insights with better algorithms, finding patterns nobody noticed initially. Because that is how astronomy works. You gather data when you can, while the target is visible, while the opportunity exists. Then you analyze it later, sometimes much later, sometimes discovering the most important details years after the initial observations. This comet gave humanity a gift, a narrow window to study material from another star system, a chance to measure composition and structure and behavior directly. We seized that opportunity completely. TESS watching for hours, Hubble capturing detailed images, Parker Solar Probe adding observations, JUICE contributing data, ground telescopes worldwide participating. The result is an incredibly rich and comprehensive dataset, one of the most detailed examinations of any interstellar object ever conducted, perhaps the most detailed until the next visitor arrives. That dataset will shape future research for decades, will guide how we search for the next object, will inform what measurements matter most, will establish benchmarks for comparison. We now know what to look for, what patterns to expect, what variations indicate rotation versus outgassing versus structural changes, what spectra reveal about composition, what brightness tells us about size and reflectivity. The lessons learned here prepare us for the next encounter, make us better observers, better analysts, better extractors of maximum information from limited data, because there will absolutely be a next encounter, and probably one after that, and many more beyond. Interstellar objects are not once-in-a-lifetime events, not rare cosmic coincidences. They are regular visitors to our solar system. We simply lacked the tools to notice them until recently. Now we have those tools, have the sensitivity, have the awareness, have the automated systems scanning for unusual trajectories. We will find more, many more, perhaps dozens in the coming decades. Each one will be unique. Each one will teach something new. Each one will expand our understanding of the galaxy and its diversity. This comet taught us about TESS's capabilities, about archival searching, about coordinated multi-spacecraft campaigns, about patience and preparation. The next one will teach different lessons, about different chemistry, different structure, different behavior, different origins. And slowly, object by object, observation by observation, we will build a comprehensive picture of interstellar space and the wanderers that drift through it. The picture is far from complete. We have barely started. 3 objects is not enough to draw firm conclusions, not enough to understand the full diversity. But we are on the right path, moving in the right direction, building the right capabilities, and that is what matters most. Here is what this comet proved beyond any possible doubt. Our solar system is not isolated, not separate, not cut off from the galactic environment. We live in a connected galaxy, a place where material moves freely between stellar systems, where isolation is illusion, where exchange is constant and ongoing. Most of the exchanged material is small like this comet, chunks of ice and rock, pebbles and boulders, things ejected by gravitational interactions, things thrown out during planetary formation, leftovers from stellar system construction. But what if larger objects get ejected too? What if entire planets can be thrown out of their home systems and sent wandering through interstellar space? Scientists think this happens regularly. Rogue planets, they call them. Worlds with no star to orbit, no source of light and heat, just cold, massive balls of rock or gas drifting alone through the void. Theoretical models predict rogue planets might actually outnumber planets with stars, might be incredibly common throughout the galaxy. Billions, perhaps trillions, floating unseen through the darkness. But they are nearly impossible to detect. No reflected starlight, no thermal emission in most cases, just cold, dark objects moving through cold, dark space. Could a rogue planet pass through our solar system? Absolutely yes, easily. And we might never notice unless it passed extremely close to something, close enough to disturb orbits, close enough to be seen by chance. This comet was not a rogue planet, just a small frozen ball, but it proves the concept works, proves objects from other systems can reach us, do reach us, will continue reaching us. That changes everything about how we think about the galaxy, about stellar systems, about cosmic connections. It means the galaxy is more dynamic than we imagined, more interconnected, more alive with movement and exchange. It means studying interstellar visitors is not just interesting curiosity, not just academic exercise. It is essential to understanding how the galaxy really works, because these travelers carry information we cannot get any other way. Information about other star systems, other stellar environments, other chemical conditions, other formation histories. And maybe they carry something even more profound. Maybe they carry something that changes our understanding of life itself. Not intelligent life, not aliens with technology and intentions, but microbes, bacteria, simple organisms frozen in the ice, dormant but viable, capable of reviving under the right conditions. Panspermia, the ancient idea that life spreads between worlds on comets and meteorites, that the building blocks of biology travel through space, that life on Earth might have originated somewhere else entirely. It sounds like science fiction, like wild speculation, but it is actually plausible, studied seriously by researchers, investigated through experiments. Some bacteria can survive in space, can endure radiation, can remain dormant for millions of years, can potentially survive embedded in ice traveling between stars. If a comet from another star system crashed on early Earth billions of years ago, could it have carried the first microorganisms, the first self-replicating molecules, the first chemical systems that would eventually evolve into all life we see today? We do not know, cannot know from current evidence. But this comet makes the question more concrete, more real, more worthy of serious consideration. Because if comets routinely move between star systems, then life could move with them, could spread, could seed new worlds, could connect biology across the galaxy. That is the ultimate implication, the ultimate possibility raised by these wandering visitors, and it is simultaneously terrifying and beautiful and completely unknown. We need more data, more samples, more visitors to study, more opportunities to test whether frozen microbes really could survive the journey. The next comet might provide answers, or the one after that, or perhaps we need to wait for actual sample return missions that bring interstellar material back to Earth for laboratory analysis. But the questions are now real. The possibilities are tangible. The implications are profound. This frozen ball of ice and rock spinning away from us might be more than just a curiosity, might be more than just a chemical sample from another stellar environment. It might be a hint about the biggest question of all. Are we alone? Or is life spread throughout the galaxy, carried on comets between the stars? We do not have the answer yet, but we are asking the question now, really asking it, seriously investigating it, and that changes everything. TESS is still up there, right now, still watching the sky, still hunting for planets around distant stars, still recording everything that moves through its vast field of view. But the mission has evolved. Scientists reprogrammed the observation schedule, added dedicated search patterns specifically designed for finding fast-moving interstellar visitors, made detecting the next cosmic wanderer an official priority, because there will definitely be another one, and another after that, and many more beyond. The question is never if, only when. When the next interstellar object appears, humanity will be ready, better prepared than for any previous visitor. Better telescopes, better algorithms, better coordination between observatories worldwide. Maybe we will catch the next one earlier in its approach, while it is still moving toward our star rather than away from it, before it makes closest approach and begins retreating. Early detection means more observation time, means better data, means deeper understanding. Maybe we will be ready to launch an intercept mission, a spacecraft already built and waiting, engines ready to fire, trajectory calculations prepared for various approach angles. Launch quickly, accelerate hard, catch up to the visitor before it escapes, deploy instruments, capture samples, return home with physical pieces of another star system. That is the ultimate goal. The dream that keeps mission planners working late into the night. The vision that drives proposals and funding requests. But even without sample return, even with just remote observations from Earth and space-based telescopes, we will learn enormously from each new visitor. Because every interstellar object is unique. Every one formed under different conditions. Every one carries different chemistry. Every one teaches something new and unexpected. This comet taught us about rotation measurement, about brightness analysis, about the power of archival searching, about coordinated observations across multiple spacecraft. The next visitor will teach different lessons, about different compositions, different structures, different behaviors, different origins. Maybe the next one will be more like Oumuamua, strange-shaped, unexpectedly accelerating, defying easy explanation, forcing us to expand our models and revise our assumptions. Maybe it will be completely ordinary, a standard comet, nothing unusual, nothing surprising. Just another data point confirming that interstellar space looks similar to our local environment. Or maybe it will be something we never imagined, something that challenges everything we think we know, something that opens entirely new questions. We cannot predict which it will be, cannot guess what the next visitor will teach us, cannot assume anything about what we will find. But we will be watching, always watching, every available telescope scanning the sky, every automated system searching for unusual trajectories, every archive being combed for objects we missed previously. The search never stops. The vigil never ends. Because the universe keeps sending messengers, keeps launching travelers on million-year journeys, keeps connecting stellar systems through wandering ice and rock. And we are finally ready to receive them, ready to observe them, ready to learn from them, ready to decode the stories they carry. This comet is leaving now, fading into the darkness, moving beyond our reach, but its legacy remains. In the data collected, in the lessons learned, in the questions raised and the answers provided and the mysteries uncovered, in the proof that we are not alone in an empty void, that we are connected to the galaxy through these ancient travelers, in the knowledge that somewhere out there, another visitor is already on its way, already approaching, already carrying new secrets and new truths. We just need to keep watching, keep searching, keep preparing for that moment when it crosses into our detection range and reveals itself. And when it does, we will be ready, more ready than ever before, with every lesson from this encounter informing how we study the next. The cycle continues, the learning compounds, the understanding deepens, one visitor at a time, one observation at a time, one discovery at a time, building toward a future where interstellar objects are routine, where sample return missions launch regularly, where we understand the galaxy through its wandering messengers. That future is coming, closer with each passing year, with each new detection, with each new tool brought online. And it starts here, with this comet, with this moment, with humanity learning to read the messages carried on frozen travelers from the stars. Think carefully about what we just witnessed together. A spacecraft designed to hunt alien planets accidentally discovered an alien comet from another star system. A visitor photographed 2 months before anyone realized what it was, hidden in plain sight in archived data, waiting to be noticed. Tracked for hours once identified. Measured precisely, analyzed thoroughly, understood deeply, all because we were watching carefully. All because we built flexible tools. All because we stayed curious and alert. That is the real lesson here. The most important takeaway from this entire story. Discovery does not happen by pure accident. It happens when preparation meets opportunity. NASA did not plan to find this interstellar comet specifically, did not build TESS expecting to track wanderers from beyond, did not design the mission around comet hunting. But when opportunity appeared, the tools existed, the capability was there, the expertise stood ready. The data got collected and archived and searched, and the result is a treasure of information. A complete picture of an interstellar visitor built from hundreds of hours of observations by dozens of instruments. That treasure will guide astronomy for years, will shape future missions, will inform search strategies, will establish baselines for comparison. Every discovery builds on previous ones. Every new finding adds to accumulated knowledge. Every visitor teaches us something that helps us study the next one better. This comet was the 3rd confirmed interstellar object, but it will absolutely not be the last, not even close. More are coming. More are already here waiting to be found. More will appear in the months and years ahead as our detection capabilities improve. Each one will be unique. Each one will bring new data. Each one will reveal something unexpected. Each one will deepen our understanding about the galaxy and its structure, about star formation and planetary systems, about the diversity of stellar environments scattered through space. Every discovery illuminates more of the cosmic landscape, makes the invisible visible, turns the unknown into the known. And we are just beginning this journey, just starting to search systematically, just developing the tools and techniques needed to find these wanderers routinely. In 10 years, we will look back at 3 detected objects and laugh. We will have dozens, maybe hundreds. A comprehensive catalogue growing longer every year. In 20 years, interstellar object detection will be routine, standard, expected, no longer newsworthy unless something truly bizarre appears. We will send missions to intercept them, return samples, analyze material in laboratories, touch pieces of other star systems with our own hands. We will study their compositions in exquisite detail, map their internal structures, understand their formation histories, trace them back to stellar origins. We will learn which types of stars produce which types of wanderers, which stellar environments eject objects most frequently, which regions of the galaxy contribute most to the interstellar population. The picture will become complete, rich, detailed, based on real data from dozens or hundreds of examples rather than speculation from 2 or 3. And that picture will transform our understanding, will change how we think about stellar systems and galactic dynamics and cosmic connections. This comet is the beginning, the opening chapter, the first page of a much longer story. A story about humanity learning to read the galaxy, about decoding messages carried on frozen travelers, about understanding our place in the cosmic whole, about discovering that we are not isolated, not separate, not alone in the void. We are surrounded by wanderers, by messengers, by connections to the rest of the galaxy, and we are finally learning to see them, to track them, to learn from them, to appreciate what they teach. The comet is leaving now, growing dimmer, fading from view, heading back toward interstellar space. But its impact remains. Its lessons persist, its data will be analyzed for years. And somewhere out there, the next visitor approaches. The next messenger travels toward us. The next chapter waits to begin. We just need to keep watching, keep searching, keep learning. The universe has so much more to show us, so many more stories to tell, so many more wonders to reveal, and we are only just beginning to listen. One more crucial thought before we continue. What if the next interstellar object is not a comet at all? What if it is something completely different? An asteroid, perhaps? Solid rock rather than ice, dark and difficult to see, tumbling through space without any visible tail or coma, or something stranger, something artificial maybe, a spacecraft, a probe, an artifact left by some other civilization exploring the galaxy. Unlikely? Yes, absolutely. Impossible? No, not at all. Because we have only observed 3 interstellar visitors so far, 3 examples out of potentially billions drifting through the galaxy. 3 samples is nowhere near enough to understand the full population. Oumuamua was bizarre, elongated, accelerating inexplicably, defying easy categorization, possibly natural, possibly something else entirely. Scientists still debate its nature, still argue about explanations, still cannot definitively say what it was, or where it came from, or why it behaved the way it did. Borisov looked like a normal comet, familiar, understandable, predictable, chemistry slightly different from solar system comets but otherwise unremarkable. This comet also appears normal, standard composition, expected behavior, nothing obviously strange beyond the simple fact of its interstellar origin. 2 seemingly normal objects and 1 mysterious anomaly. What does that tell us about the broader population? Not very much, honestly. We need larger sample sizes, more examples, more data points, more diversity in our observations. And that diversity might include things we never anticipated, objects that challenge our categories, travelers that defy our expectations, discoveries that force us to revise our models. The next visitor might surprise us completely, might be something nobody predicted, might open entirely new areas of research. That is the exciting part, the thrilling possibility. The reason scientists stay up late, scanning data and searching archives, because you never truly know what you will find until you actually look, cannot predict what waits just beyond current detection limits, cannot assume the future will resemble the past. Every new discovery has potential to surprise us, to challenge us, to change everything we thought we understood. That is the fundamental beauty of science. You prepare for the expected, build tools for known possibilities, train for likely scenarios, but you remain open to the unexpected, ready for surprises, willing to revise everything when new data demands it. Maybe the next interstellar visitor will be exactly what we expect. Another comet, another ball of ice and rock, another wanderer carrying chemistry from a distant stellar nursery. Or maybe it will be something that makes us question everything, something that forces entire fields to rethink their foundations, something that opens paths nobody imagined existed. We cannot know in advance, cannot predict with certainty, can only wait and watch and prepare. And when it arrives, whatever it is, we will study it with every tool available. We'll extract every possible piece of information. We'll learn everything we can before it vanishes again into the darkness. Because that is what we do. That is humanity's gift. Curiosity, investigation, the relentless drive to understand. The comet taught us that drive pays off, that preparation matters, that watching carefully reveals wonders. The next visitor will teach us something else, something new, something unexpected, and we will be ready for it, as ready as we can be, with open minds and sharp tools and endless curiosity, waiting for the universe to show us what comes next. The data from this interstellar comet sits publicly accessible right now. Anyone can download it. Anyone can analyze it. Anyone with internet access and basic programming skills can explore the observations. That is how modern science works. Open, collaborative, transparent, no secrets, no hidden data, everything available for independent verification and analysis. One team discovers something, publishes their findings, shares the raw data. Others examine it, test the conclusions, build on the work, refine the understanding. And the collective result is faster progress, better science, more complete pictures, fewer mistakes surviving peer review. This comet belongs to everyone, not just professional astronomers, not just people with PhDs, not just researchers at major institutions. Amateur astronomers can access the data. Students learning image processing can practice on real observations. Citizen scientists can contribute discoveries. Some of the most important astronomical findings come from unexpected sources: amateur astronomers, hobbyists, students, people outside traditional academic structures. Gennady Borisov discovered the second interstellar object, not working at a major observatory, not using billion-dollar equipment, just someone with a good telescope and dedication and sharp eyes. That discovery changed astronomy forever. Proved interstellar objects visit regularly, opened entire research programs, all because one person was watching carefully. This comet could spark similar discoveries. Someone might find something in the data that professionals missed, some pattern nobody noticed initially, some correlation that reveals new physics. The possibility exists because the data is open, because anyone can look, because science values contributions from all sources, regardless of credentials. That openness accelerates progress enormously, brings fresh perspectives, catches mistakes, finds connections nobody expected. It also inspires the next generation, students seeing real data from real discoveries, learning how professional research works, getting excited about science and exploration. Maybe someone reading this will download the Comet data tonight, will load it into analysis software, will find something interesting, will contribute to human knowledge. That is the power of open science. It democratizes discovery, makes participation possible for anyone with curiosity and determination. And the more people participate, the more we discover. The more eyes examining data, the fewer things slip through unnoticed. The more minds thinking about problems, the faster solutions emerge. This comet's data will be analyzed for decades, long after the object itself has faded from view, long after it has left our solar system completely, long after it has returned to the interstellar void, because data never expires, never stops being useful, always contains potential for new insights when examined with new techniques or fresh perspectives. 10 years from now, someone might develop a new analysis method, apply it to this archival data, discover something nobody noticed in 2026. 20 years from now, machine learning algorithms might extract patterns currently invisible to human researchers, reveal correlations nobody thought to search for. That is the beauty of permanently archived observations. They keep giving, keep teaching, keep revealing new truths as our tools and understanding improve. Every photon TESS captured from this comet carries information. Every pixel in every image contains data, and we might not fully understand what all that data means for years or decades. But it exists, available, waiting, ready for anyone curious enough to examine it. That is the legacy this comet leaves behind, not just scientific papers and news articles, but actual raw observations that anyone can explore. Democratized discovery, open science, shared human knowledge growing through collaborative effort. And somewhere in that data might be secrets nobody has found yet, patterns nobody noticed, truths nobody realized, waiting for you to discover them. So, where do we go from here? What happens next in humanity's relationship with interstellar visitors? We keep watching, keep searching systematically, keep building better detection capabilities, keep improving our tools and techniques. We construct more sensitive telescopes, develop smarter algorithms, create automated systems that scan the sky constantly without human intervention. We prepare actual missions, spacecraft designed specifically to intercept interstellar objects, fast ships capable of matching velocities with targets moving at dozens of miles per second, ships carrying drills and sample collectors, laboratories for on-site analysis, return vehicles capable of bringing pieces back to Earth. And we wait for the next visitor to appear, the next opportunity, the next cosmic messenger bringing samples from beyond, because that visitor is definitely coming, already traveling toward us, already on a trajectory that will bring it close enough to detect. Maybe months away, maybe years, maybe decades, but coming inevitably. And when it arrives, we will be more ready than ever before, with every lesson from this comet informing our approach, with every technique refined through practice, with every capability enhanced through experience. We will detect it earlier, track it more completely, measure it more precisely, understand it more deeply. Each visitor builds on lessons from previous ones. Each discovery makes the next one easier to study. Each observation refines our collective expertise. The learning compounds. The capability grows exponentially. The understanding deepens with each iteration. In 10 years, we might have observed 20 interstellar objects, built comprehensive catalogues, identified patterns and categories, started understanding the full diversity. In 20 years, we might return actual samples, bring pieces of another star system back to Earth, analyze alien material in laboratories, touch interstellar travelers with our own hands. In 30 years, interstellar object studies might be routine, standard, expected, no longer making headlines unless something truly extraordinary appears. That future requires continued commitment, sustained funding, long-term planning, dedication to patient observation and systematic searching. But the payoff is profound. Complete transformation of our understanding, connection to the wider galaxy through physical samples and detailed observations, knowledge about how star systems differ, about what conditions produce what kinds of objects, about the diversity of stellar environments throughout our galactic neighborhood. Answers to questions we can barely formulate yet, solutions to mysteries we have not even identified, insights that emerge only from accumulating many examples and finding patterns. This comet started that process, contributed one crucial data point, added its information to the growing database. The next visitor will contribute another piece, and the one after that another, and slowly the picture will emerge of a galaxy alive with movement, full of exchange, connected through wandering travelers carrying material between stars, of stellar systems that are not isolated islands but connected communities sharing material across vast distances over enormous timescales, of a cosmos more dynamic and interconnected than we ever imagined when we thought our solar system stood alone in empty space. That transformed understanding begins here, with this comet, with this discovery, with this moment of recognition. We are not alone in the void. We are surrounded by messengers from other stellar environments. We are part of a connected galactic ecosystem, and we are just beginning to understand what that means. Before moving forward, look one more time at what actually happened here. Review the full scope of this discovery. A planet-hunting satellite spotted an interstellar comet entirely by accident, captured it moving across star fields, measured its brightness for hours, revealed its rotation through careful analysis. Then astronomers searched archives and found it had been photographed months earlier, before anyone knew it existed, before anyone recognized what they were seeing. Multiple spacecraft across the solar system contributed observations: Hubble, Parker Solar Probe, JUICE, ground-based telescopes worldwide, all coordinating, all adding unique data. Researchers extracted rotation periods from brightness variations, chemical compositions from spectroscopy, structural information from light curves and imaging. They built the most comprehensive dataset of any interstellar visitor so far, archived everything publicly, made it available to anyone interested in studying it further. All because people were watching carefully, because systems existed to catch unexpected discoveries, because science values flexibility and preparation. The comet could easily have been missed entirely, could have slipped past unnoticed, could have remained just another faint dot in billions of archived images. But someone was paying attention, someone looked carefully, someone recognized that something unusual was happening. That vigilance paid off enormously. Turned a potential non-event into a major discovery, transformed overlooked data into groundbreaking science. And that pattern will repeat with future visitors. Many will be obvious, bright, unmistakable, easy to recognize immediately. But some will be subtle, faint, easy to overlook, requiring careful searching and patient analysis to identify. Those subtle ones might be the most interesting, might teach the most valuable lessons, might carry the most surprising revelations. Finding them requires the same dedication shown here, the same careful attention, the same thorough examination of data, the same willingness to search archives, to stack images, to filter noise, to recognize patterns others missed. That dedication is what separates discovery from oversight. What transforms data into knowledge? What turns observations into understanding? This comet demonstrated that process perfectly, showed how modern astronomy really works, how discoveries emerge from coordinated effort and careful analysis. One person notices something unusual, alerts others, teams form, multiple telescopes observe. Data gets shared, analysis proceeds, understanding emerges. Not one brilliant individual making a solitary breakthrough, but collaborative effort building knowledge collectively. Many minds working together, many tools applied simultaneously. That is how science advances in the 21st century, through coordination, through sharing, through combining expertise and resources. This comet succeeded because multiple teams worked together, because data flowed freely, because everyone contributed what they could, and that collaborative model will only grow stronger. Better communication tools, better data sharing platforms, better coordination between observatories, leading to faster discoveries, deeper understanding, more complete pictures of cosmic phenomena. The next interstellar visitor will benefit from even better coordination, even more participating telescopes, even smoother data sharing and analysis. And the one after that will be even better studied, even more thoroughly observed, even more completely understood. Each success builds infrastructure for the next. Each discovery refines the process. Each observation strengthens the collective capability, until finding and studying interstellar objects becomes routine, expected, standard procedure rather than exciting breakthrough. That future is coming, built on foundations laid by observations like these, by discoveries like this comet, by the dedicated work of countless researchers contributing pieces to the larger puzzle. We are watching that future emerge, watching science evolve, watching capability grow, and it starts here, with careful attention, with thorough analysis, with collaborative effort, with refusing to let cosmic messengers slip past unnoticed. Here is the final undeniable truth about this wandering traveler from the stars. It represents proof, hard evidence, undeniable demonstration of multiple facts about our universe. Proof that interstellar objects exist. They are real, not theoretical, not speculative. Actual physical travelers moving between stellar systems, proof that we possess the capability to detect them. Our telescopes work, our techniques function, our search strategies succeed. Proof that we can learn from them, can measure compositions, can determine structures, can extract meaningful information from distant observations. And proof that our solar system connects to the wider galaxy, that we are not isolated, not separate, not cut off from cosmic material flows. That proof matters enormously, because it transforms abstract ideas into concrete reality, changes speculation into established fact, replaces uncertainty with knowledge. We used to wonder whether interstellar objects visit our solar system. Now we know they do. Have documented 3 examples, we'll find many more. We used to question whether we could detect such visitors. Now we know we can. Have demonstrated the capability repeatedly, can improve it systematically. We used to debate whether studying them would teach us anything valuable. Now we know it does. Have extracted rich datasets. We'll learn even more from future examples. That is the power of real data, of actual observations, of concrete evidence rather than theoretical models. Data never lies, cannot be argued away, either exists or does not, either shows something or does not, and the data from this comet shows clearly and definitively that our detection systems work, our observational techniques succeed, our analytical methods extract truth, our models describe reality accurately enough to make useful predictions. That is science functioning exactly as designed, making observations, testing hypotheses, gathering evidence, building understanding through careful systematic investigation. The comet provided an opportunity, science seized it, knowledge increased, understanding deepened, simple, direct, effective, beautiful in its clarity. And it opens doors to questions we could barely ask before, questions that require evidence before they become meaningful, questions about stellar system diversity, about chemical variations across the galaxy, about how star formation differs in different environments, questions about material exchange, about whether life could spread on comets, about biological connections across interstellar distances, questions about what else might be drifting through the galaxy, what else might visit, what else might teach us about cosmic connections. Those questions need answers, real answers based on actual data from multiple examples. This comet provides one data point toward those answers, one example, one sample, one piece of the larger puzzle. Not enough to answer everything, not sufficient to settle all debates, but enough to prove the questions are worth asking, enough to demonstrate that answers are possible, enough to justify continued searching and observation. That is progress, real scientific progress, built on evidence, driven by data, advancing through systematic investigation. The comet proved we are on the right track, doing the right things, asking the right questions, building the right capabilities. And that proof matters, validates the effort, justifies the investment, encourages continued dedication, because now we know for certain, know beyond doubt. Interstellar visitors are real. We can find them, we can study them, we can learn from them, and each one teaches us something profound about the galaxy we inhabit. That knowledge changes how we see ourselves, how we understand our place in the cosmos, how we relate to the vast universe surrounding us. We are not alone, not isolated, not separate from the cosmic whole. We are connected. Through these frozen travelers, through these wandering messengers, through these ancient samples from distant stellar environments, connected to the galaxy, to its history, to its diversity, to its endless cycles of formation and destruction and renewal. The comet proved that connection is real, measurable, undeniable, and that changes everything. Let me pose one more challenging question, one more thought to consider carefully before we continue. What if the next interstellar object is not a natural formation? What if it shows signs of artificial construction? What if evidence suggests intelligent design? Before dismissing that as wild speculation, consider the logic carefully. We have observed exactly 3 confirmed interstellar visitors, 3 samples from potentially billions of such objects drifting through the galaxy. 3 is nowhere near enough to characterize the full population, not nearly sufficient to understand complete diversity, not adequate to rule out rare but significant categories. Oumuamua remains unexplained. Its acceleration defies simple natural models. Its shape seems unlikely for random formation. Its behavior raises legitimate questions. Some scientists proposed natural explanations: outgassing, unusual composition, strange structure, all possible, all plausible within known physics. Others suggested artificial origins, a light sail perhaps, a probe designed by another civilization, technology exploring the galaxy, also possible, also consistent with observations. The debate remains unsettled. Data is insufficient to prove either explanation definitively. Both camps present reasonable arguments. Neither has been conclusively ruled out. What happens when the next mysterious object appears? When another visitor defies easy categorization? When observations cannot be explained by natural processes alone? Do we assume natural origins by default? Do we require extraordinary evidence before considering alternatives? Do we remain open to possibilities that challenge our assumptions? Those are difficult questions. Questions science must grapple with honestly. Questions that deserve serious consideration rather than reflexive dismissal. The universe is vast, contains billions of stars, trillions of planets potentially. If even a tiny fraction developed intelligent life, technological civilizations could be common. And technological civilizations might send probes, might explore their galactic neighborhood, might launch thousands or millions of spacecraft to investigate nearby stars. Some of those probes might pass through our solar system, might be moving slowly enough to observe carefully, might show characteristics distinguishing them from natural objects. We should be prepared for that possibility, should have frameworks for evaluating evidence, should think carefully about what would constitute convincing proof of artificial origins. Not jumping to conclusions prematurely, not seeing aliens in every unusual observation, but also not dismissing possibilities before examining evidence thoroughly. Good science remains open to all explanations, tests each against available data, accepts whichever fits best regardless of implications. If future observations indicate artificial construction, science must follow that evidence wherever it leads, must investigate thoroughly, must verify carefully, must accept truth even when surprising. The next interstellar visitor might be exactly what we expect: another comet or asteroid, another natural object, another sample from stellar system formation. 99 times out of 100 that will probably be the case. Natural, unremarkable, expected. But that 100th time? That rare exception? That one visitor that shows clear signs of design? We must be ready for it, must have protocols in place, must know how to respond, must be prepared to recognize something truly extraordinary if it appears. This comet taught us those lessons, taught us to watch carefully, to measure precisely, to remain open to unexpected discoveries. The next visitor might teach us something even more profound, something that challenges everything we think we know about our place in the universe, and we need to be ready for that possibility. Ready intellectually, ready scientifically, ready psychologically, because the universe contains more wonders than we have imagined, more possibilities than we have considered, more surprises than we expect. And the next one might be just beyond current detection limits, already approaching, already carrying revelations that will transform human understanding forever. We just need to keep watching, keep measuring, keep analyzing, keep remaining open to whatever truth reveals itself. The data from this interstellar comet exists in archives right now, permanently, accessible to anyone with interest and basic technical skills. That permanence matters enormously. Future researchers will access these observations, will analyze them with techniques not yet invented, will discover patterns nobody notices today. Because technology improves constantly, analytical methods evolve, understanding deepens. What seems ordinary today might reveal extraordinary insights tomorrow. 10 years from now, someone might develop breakthrough analysis software, apply it to this archived data, discover correlations invisible to current techniques. 20 years from now, artificial intelligence systems might process these observations, extract patterns too subtle for human perception, reveal physics we do not understand yet. The data never expires, never loses value, always contains potential for new discoveries when examined with fresh eyes and better tools. That is why archiving matters so much, why making observations publicly available serves science so well, why open data policies accelerate discovery. This comet might teach lessons we do not discover for decades, might contain information we cannot extract with current capabilities, might hold answers to questions we have not asked yet. But the data exists, waiting, ready, available when we develop tools sophisticated enough to decode it fully. Future astronomers will look back at these observations with amazement, will marvel at how much we missed initially, will find treasures hidden in plain sight. Just like we found the comet itself hidden in May observations, just like we discovered it was there all along waiting to be noticed. The same pattern will repeat with the data. Hidden patterns waiting for discovery, subtle correlations requiring advanced analysis, truths buried beneath surface-level observations. Every archived dataset contains more than we extract initially, more than we notice at first glance, more than we can process with current understanding. That is why permanent public archives matter so profoundly, why NASA makes everything accessible, why science values transparency and open data. Because knowledge builds on itself, each generation standing on shoulders of previous ones, each advance enabling further advances, each discovery making the next one possible. This comet's data will contribute to breakthroughs we cannot imagine today, will enable discoveries we do not know we need yet, will teach lessons that seem impossible currently. But only if the data survives, only if it remains accessible, only if future researchers can examine it freely. That is the commitment NASA made, the promise science makes. The foundation of cumulative human knowledge. Observe carefully, record thoroughly, archive permanently, share openly, enable future discovery. Simple principles, profound implications, exponentially increasing returns over time. This comet benefits from those principles, contributes to them, demonstrates their power. Future visitors will benefit even more, will be studied even more thoroughly, will teach even greater lessons, all because we commit to permanent open archives, to data that never disappears, to observations that remain useful forever. That commitment defines modern astronomy, separates current science from historical approaches, enables acceleration impossible in previous eras. And it starts here, with observations like these, with data carefully collected and thoroughly archived, with commitment to openness that serves all humanity. The comet is leaving, fading from view, becoming too dim to observe directly, but its data remains permanent, accessible, ready, waiting for future minds to discover what we missed, waiting for better tools to extract hidden truths, waiting for questions we have not thought to ask yet. That is its final gift to science, not just what we learned already, but what we will learn decades from now, what future researchers will discover in archived observations. Knowledge that compounds, understanding that grows, discovery that never ends. all enabled by commitment to permanent public data archives, all made possible by principles of open science, all serving the collective advancement of human knowledge. So, what ultimate conclusion can we draw from everything we have witnessed together? What final truth emerges from this cosmic encounter? We live in a connected galaxy. That is the core lesson, the fundamental revelation, the truth that changes everything. Our solar system does not exist in isolation, does not float alone through empty space, does not remain separate from the wider cosmos. Material flows between stellar systems, objects travel from star to star, connections exist across enormous distances and timescales. This comet proves that flow is real, demonstrates those connections physically, shows us tangible evidence of galactic interconnection. Most of the flowing material consists of small objects like this comet, chunks of ice and rock, pebbles and boulders, leftovers from planet formation, debris ejected by gravitational interactions. But the flow itself matters more than individual objects. The principle more than specific examples, the connection more than particular travelers, because those connections mean our solar system participates in galactic processes, exchanges material with neighboring stars, contributes to and receives from the larger cosmic environment. We are not isolated, not separate, not independent from galactic dynamics. We are part of something vast, something ancient, something ongoing and eternal. Material ejected from our system eventually reaches other stars. Material from other stars eventually reaches us. The exchange flows constantly in all directions. Over billions of years, that exchange adds up, influences compositions, affects chemical inventories, shapes what materials are available for planet formation, maybe even transports life, maybe spreads biology across interstellar distances, maybe connects living worlds through frozen travelers carrying dormant microbes. That remains speculative, unproven, hypothetical, but possible, worth investigating, deserving serious scientific attention. This comet makes those investigations meaningful, makes the questions concrete, provides actual examples to study rather than pure theory. And every future visitor will add more data, more examples, more evidence about how galactic exchange actually works. Slowly, we will build complete understanding. We'll map the flows. We'll characterize the populations. We'll quantify the exchange rates. We'll learn which stellar environments eject material most readily, which objects survive interstellar transit best, which compositions are most common. We'll discover whether biological material really can spread this way, whether life might be galactic rather than planetary, whether Earth's biology might have originated elsewhere. Those are profound questions, revolutionary possibilities, ideas that transform how we understand our existence. This comet opens the door to investigating them, proves the questions are worth asking, demonstrates that answers are accessible through careful observation. That is its ultimate legacy, not just what we learned about one specific object, but what that object taught us about asking bigger questions, about our connection to the galaxy, about flows between stars, about participation in cosmic processes, about being part of something enormous and ancient and ongoing. We are not alone in empty space. We are embedded in a dynamic galactic ecosystem. We are connected through countless frozen travelers moving between stars. That truth changes how we see ourselves, how we understand our origins, how we imagine our future. We are not isolated Earth, not separate solar system, not disconnected island floating alone. We are part of the galaxy, shaped by it, connected to it, participating in its endless cycles. This comet proved that connection beyond doubt, demonstrated it physically, made it undeniable and real. And that changes everything about how we understand our place in the universe. One final thought to leave with you as we approach the end of this journey together. Right now, as you listen to these words, another interstellar object is traveling toward our solar system, already on its way, already crossing the vast distances separating stars. We do not know it exists yet, have not detected it, have not noticed it moving through our telescope fields, but it is coming, inevitably, certainly, just a matter of time before it crosses into detection range and reveals itself. Maybe months away from discovery, maybe years, maybe decades, but approaching constantly, never stopping, never slowing. Somewhere out there, in the darkness between stars, frozen material drifts steadily toward us, carrying chemistry from another stellar environment, bringing samples from another world, moving on a trajectory that will eventually bring it close enough to observe. And when it arrives, when it finally becomes visible, when we finally recognize what we are seeing, all the lessons from this comet will guide our response. We will detect it earlier because we know what to look for. We'll track it more carefully because we understand what matters. We'll measure it more precisely because we refined our techniques. We'll coordinate observations better because we practiced with this visitor. We'll extract more information because we learned from previous examples. We'll understand it more deeply because knowledge builds on itself. Each visitor prepares us for the next. Each discovery makes future ones easier. Each observation sharpens our collective expertise. The learning compounds exponentially. Capabilities grow faster than linear time. Understanding deepens with each iteration. In 5 years, we might detect 5 more interstellar objects. In 10 years, perhaps 20. In 20 years, maybe hundreds. Each one unique, each one carrying different information, each one teaching something new about stellar environments and galactic dynamics and cosmic connections. Together, they will paint a comprehensive picture, will map the interstellar population, will characterize the flow of material between stars, will reveal patterns invisible from single examples. That future begins here, with this comet, with these observations, with these first careful steps toward understanding. Every journey starts with single steps. Every revolution begins with small changes. Every transformation builds from initial efforts. This comet represents one of those initial efforts. One early step, one beginning of something much larger. A beginning of systematic interstellar object studies, of routine detection and tracking, of comprehensive characterization, of understanding built from many examples rather than speculation from few. That systematic approach will transform astronomy, will connect stellar system science to galactic dynamics, will bridge scales from individual worlds to cosmic evolution, will show us how material flows through space, how chemistry varies across the galaxy, how environments differ between stellar nurseries, will teach us about our origins, about where Earth's material came from, about what processes shaped our chemical inventory, about whether our system is typical or unusual, will maybe even teach us about life, about whether it spreads, about whether biology is planetary or galactic, about whether we are alone or part of something much larger. Those lessons wait in the future. Wait for more data. Wait for more visitors. Wait for more observations. But they are coming. Approaching. Inevitable. Because the galaxy keeps sending travelers, keeps launching frozen messengers on million-year journeys, keeps connecting stars through wandering ice and rock, and we are finally ready to receive them, ready to observe them carefully, ready to learn everything they can teach. This comet showed us how, demonstrated the process, proved the concept. Now we apply those lessons to every future visitor, build on this foundation, expand our understanding systematically. The next traveler approaches, the next mystery awaits. The next chapter of humanity's cosmic story prepares to begin. We just need to keep watching, keep searching, keep learning. The universe has so much more to reveal, so many more travelers to send, so many more connections to demonstrate, and we are only just beginning to see them. If this journey through the cosmos fascinated you, if learning about interstellar visitors sparked your curiosity, then there is so much more to explore. More comets waiting to be discovered, more data waiting to be analyzed, more questions waiting to be investigated. The universe overflows with wonders we are only beginning to notice, phenomena we are just starting to understand, connections we are barely beginning to recognize. Every discovery opens new questions. Every answer reveals deeper mysteries. Every observation enables further observations. This comet represents one small piece of an enormous puzzle, one data point in a vast dataset, one example among countless billions. But every piece matters. Every data point contributes. Every example teaches something valuable. And you can participate in this exploration, can contribute to this growing understanding, can be part of humanity's cosmic journey. Follow the research as it develops. Read scientific papers as they publish. Watch for announcements of new discoveries. Or dive deeper. Download the actual data. Learn analysis techniques. Practice on real observations. Develop your own insights. Or simply stay curious. Keep asking questions. Keep wondering about what lies beyond. Keep imagining possibilities. Because curiosity drives everything, fuels discovery, enables progress, pushes boundaries. The scientists studying this comet started with curiosity, with questions, with wonder about what might be drifting through interstellar space. That curiosity led to systematic searching, to careful observations, to detailed analysis, to deep understanding. And that same curiosity will drive future discoveries, will find the next visitor, will uncover the next mystery, will reveal the next cosmic truth. You can be part of that process, can contribute that curiosity, can help push human knowledge forward. Maybe by becoming a professional astronomer, maybe by supporting science through advocacy and funding, maybe simply by staying engaged and interested. All of it matters, all of it contributes, all of it helps advance collective understanding. This comet showed us that advancement is possible, that questions have answers, that mysteries yield to systematic investigation. The next visitor will reinforce those lessons, will demonstrate them again, will prove them repeatedly, and slowly, observation by observation, discovery by discovery, we will build complete understanding of our galactic neighborhood. We'll learn where we came from, how we fit in, what connections exist, what future awaits. Those answers emerge through sustained effort, through continued curiosity, through never stopping the search for truth. So keep asking questions, keep seeking answers, keep wondering what lies beyond current understanding. The universe rewards curiosity, reveals secrets to persistent investigators, shares wonders with those patient enough to observe carefully. This comet proved that, demonstrated it beautifully, showed us what careful observation can achieve. The next discovery will prove it again, and the one after that, and countless more beyond, building toward a future where we understand our cosmic context completely, where we know our origins definitively, where we recognize our connections thoroughly. That future approaches, closer every day, built on foundations laid by discoveries like this one, and it starts with curiosity, with questions, with wonder, with looking up at the night sky and asking what is out there, what visits us, what connects us to the rest of the cosmos. The comet answered some of those questions, raised new ones, pointed toward deeper mysteries. Now we continue the journey, keep searching, keep discovering, keep learning. The universe has so much more to show us, so many more stories to tell, so many more wonders to reveal, and we are only just beginning to listen. Thank you for traveling through this cosmic story with me, for exploring the journey of an interstellar visitor, for learning about humanity's third encounter with material from beyond our stellar neighborhood. This comet is small in cosmic terms, just a frozen ball of ice and rock, a few miles across, insignificant compared to planets and stars and galaxies. But its implications are enormous, its lessons profound, its impact on human understanding potentially revolutionary, because it proves beyond doubt that we are not alone in empty space, not isolated, not cut off from the rest of the galaxy. We are connected, through frozen travelers, through wandering messengers, through ancient samples from distant stellar environments, connected to stars we will never visit, to worlds we will never see, to processes that began billions of years before Earth formed. That connection matters more than any single discovery, matters more than specific measurements, matters more than individual data points, because it changes our fundamental understanding of our place in the universe, changes how we see ourselves, changes what we imagine is possible. We are not separate Earth, not isolated solar system, not independent island floating alone through cosmic void. We are part of the galaxy, shaped by it, connected to it through countless threads of material exchange and gravitational interaction and shared history. This comet made that connection tangible, made it visible, made it undeniable, and in doing so, changed everything about how we understand our cosmic context. The comet is leaving now, fading from our view, heading back toward interstellar space on a journey that will last millions of years more. We will never see it again, never observe it directly, never know where its journey ultimately ends. But its data remains, its lessons persist, its impact continues. In archives that will be studied for decades, in techniques that will be refined and improved, in questions that will drive future research, in the proof that we are connected to something vast and ancient and ongoing. So if you enjoyed this exploration, if learning about cosmic visitors sparked your interest, hit that like button and subscribe, because more visitors are coming, more stories await, more cosmic mysteries will reveal themselves, and I will be here to share them with you, to explore them together, to learn what the universe has to teach. The next interstellar traveler is already on its way, already crossing the void, already carrying new secrets and new truths. We just have not seen it yet, have not detected its approach, have not recognized its presence. But we will. When it gets close enough, when it crosses into our detection range, when we finally notice what has been approaching all along, and when that happens, you will be among the first to know, among the first to learn, among the first to explore what it teaches. Until then, keep looking up, keep asking questions, keep wondering about what lies beyond. The universe has endless wonders to reveal, endless stories to tell, endless connections to demonstrate. We have only just begun to see them, to understand them, to appreciate what they mean. This comet was one chapter in a much longer story, one page in an enormous book, one glimpse of something vast and profound. More chapters await, more pages will turn, more glimpses will illuminate the cosmic landscape. Thank you for joining me on this journey, for exploring this mystery, for learning about our third confirmed visitor from the stars. More adventures await, more discoveries approach, more wonders will reveal themselves. Keep watching the skies, keep following the science, keep exploring the universe, because we are only just beginning to understand the galaxy we live in, only starting to recognize the connections that bind us to the cosmos, only beginning to read the messages carried on frozen travelers from distant stars. The journey continues, the exploration never ends, the learning compounds forever, and somewhere out there, the next visitor approaches, the next mystery awaits, the next revelation prepares to transform our understanding. We just need to keep watching, keep searching, keep learning, The universe has so much more to show us, and we are ready to see it.